Welcome to G Fun Facts Online. Today we are going to dismantle your intuition about empty space. We are going to talk about the hunt for a ghost that has haunted physics for half a century. It is a story about the definition of reality, the relativity of temperature, and how a choir of atoms might finally allow us to hear the universe scream. Let's begin with a simple concept that turns out to be a lie: the vacuum. In classical physics, if you take a box and pump out every single atom, shield it from every photon, and cool it to absolute zero, you have a vacuum. You have a stage with no actors. It is empty, it is silent, it is dead. But in the world of quantum field theory, or QFT, this version of nothingness does not exist. According to QFT, the fundamental building blocks of the universe are not particles, they are fields. Think of the electron not as a tiny marble, but as a ripple in an invisible ocean that permeates the entire universe. When that ocean is still, we say there are no electrons. But here is the catch: the ocean can never be perfectly still. The Heisenberg uncertainty principle forbids a quantum field from having exactly zero energy and exactly zero change simultaneously. So the vacuum creates compromise. It fluctuates, it roils with activity. In every cubic centimeter of empty space, pairs of virtual particles, matter and antimatter, are constantly snapping into existence, borrowing energy from the void, and annihilating each other in a time frame so short that time itself barely registers them. This is the quantum vacuum. It is not empty space, it is a seething potential ocean. It is a medium, thick with energy pressing against everything. Now, for decades, physicists have asked a terrifying question. What happens if you run through this ocean fast enough? If you are floating freely in space, these fluctuations cancel out. You see darkness. You feel cold. This is what we call the Minkowski vacuum. But in the 1970s, three physicists, Stephen Fulling, Paul Davies, and William Unruh, discovered a paradox that broke this symmetry. They realized that the concept of a particle and the concept of temperature are not absolute facts of nature, they are relative. They depend on how you move. If you begin to accelerate through this quantum vacuum, you change the game. Your acceleration creates a horizon, known as a Rindler horizon, which traps information behind you, much like the event horizon of a black hole hides the interior from the outside universe. This separation of information disrupts the delicate cancellation of those virtual particles. To an accelerating observer, the vacuum fluctuations stop looking like random noise. They organize, they solidify. If you accelerate hard enough, the cold, dark vacuum ignites. You would no longer see darkness. You would see a blinding, warm bath of thermal radiation. You would feel heat coming from nowhere. This is the Unruh effect. The realization that acceleration literally warms the vacuum. It implies that the very existence of particles depends on the observer. To a stationary astronaut, space is empty. To an astronaut accelerating alongside him, that same space is full of hot radiation. Both are correct. This prediction is elegant, profound, and for the last 50 years it has been completely useless to experimentalists. It has remained a mathematical ghost. Why? Because of the numbers. The formula for the Unruh temperature involves Planck's constant, the speed of light, and Boltzmann's constant. The speed of light is huge, and Boltzmann's constant is tiny, which means the universe is fighting you. To warm the vacuum by just 1 single degree Kelvin, which is still colder than deep space, you would need to accelerate at 10 to the power of 20 meters per second squared. Let's put that in perspective. A fighter pilot passes out at 10 gigaseconds. To see the Unruh glow, you would need to reach the speed of light in less than a microsecond. You would need a thermometer that could survive being crushed by the force of 1 trillion suns. For decades, the Unruh effect was considered a thought experiment, something valid only on chalkboards. Experimentalists joked that you would have to wait longer than the age of the universe to see a signal, or build a particle accelerator the size of the galaxy. The signal is too weak, and the background noise of the universe is too loud. It was a whisper in a hurricane. But this is where the story shifts. In the 2020s, a revolutionary new theoretical framework emerged. Physicists realized that if we cannot create the brutal acceleration required to heat a single atom, perhaps we can change the way we listen. Instead of trying to force a single soldier to shout louder, what if we recruited a choir? This is the dawn of cooperative Unruh detection. The breakthrough relies on a phenomenon known as Dix superradiance. Imagine a single atom in a vacuum. If it is excited, it will eventually emit a photon and drop to a lower energy state. This is a random, lonely process. But now, imagine placing a cloud of atoms between two perfect mirrors. These atoms interact not just with the vacuum, but with each other, mediated by the light bouncing between the mirrors. If you space them correctly, something magical happens. They stop acting as individuals. They lock phases. They sync up. They become a single, collective quantum entity, a macro atom. When this collective entity emits light, it doesn't do so randomly. It emits a blinding, intense pulse of light, a super radiant burst. It is the difference between 1,000 people whispering out of sync and 1,000 people shouting the exact same word at the exact same moment. Researchers from Stockholm University, IISER Mohali, and other institutions discovered that this super radiant burst is incredibly sensitive to the environment. They found that the warmth of the Unruh effect, even if it is infinitesimally faint, acts as a trigger. If you accelerate this system of atoms, or effectively simulate the acceleration, the faint thermal bath of the Unruh radiation interacts with the collective state. It disturbs their synchronization just enough to change when the burst happens. Specifically, the Unruh effect causes the super radiant flash to occur earlier than it would in a cold vacuum. This is the genius of the cooperative method. We do not need to measure a tiny temperature change, which is incredibly difficult. We do not need to detect a faint photon against a bright background. We only need to measure time. Imagine two scenarios. In scenario A, the atoms are stationary. The super radiant burst happens at exactly 1 second. In scenario B, the atoms are accelerating. The Unruh effect warms them slightly. The burst happens at 0.99 seconds. That tiny shift in time is the clean signature. It is a time-stamped flash. By looking for the burst to arrive early, experimentalists can filter out all the classical noise and isolate the pure quantum signal. The whisper of the Unruh effect triggers the shout of the superradiance. But the innovation doesn't stop there. Parallel to the choir approach, another groundbreaking proposal from MIT and the University of Waterloo has offered a complementary path called stimulated Unruh detection. The team, including Vivek Sudhir and Barbara Soda, tackled the noise problem from a different angle. Usually, if you accelerate a particle to these speeds, you create all sorts of classical electromagnetic noise that drowns out the quantum glow. Their solution is something called acceleration-induced transparency. They calculated a specific trajectory for an electron, a precise dance through a field of light that renders the classical noise invisible. By manipulating the electron's path, they can make the detector transparent to the standard radiation that usually swamps the signal. When the classical noise is cancelled out, the only thing left to see is the Unruh radiation. It is like putting on noise-canceling headphones that silence a jet engine so you can hear a pin drop. They propose stimulating the vacuum with lasers, essentially tickling the quantum field to release more Unruh photons than it naturally would, amplifying the probability of detection from once in a universe to something we can see within hours in a lab. So why does this matter? Why are thousands of physicists chasing this glow? Why build complex cavities and laser arrays just to see a tiny flash of light? The answer lies in the darkness of black holes. The Unruh effect is the flat space twin of Hawking radiation. Stephen Hawking predicted that gravity creates an event horizon that peels the vacuum apart, creating thermal radiation. William Unruh predicted that acceleration creates a Rindler horizon that does the exact same thing. Observing the Unruh effect is observing the mechanism of Hawking radiation in a lab without needing to visit a black hole. It confirms that the vacuum is structured by horizons, a key concept in understanding how the universe stores information. Furthermore, this is about the crisis of modern physics. We still do not have a theory of everything. General relativity, which describes gravity, and quantum mechanics, which describes particles, hate each other. They break down when combined. The Unruh effect is one of the few phenomena where these two theories shake hands. It uses the math of relativity acceleration and horizons, and the math of quantum mechanics fields and virtual particles to predict a single, observable outcome. Proving it is real proves that our tentative steps toward quantum gravity are on the right path. It also has massive implications for quantum information. The Unruh effect implies that entanglement is observer-dependent. Two particles that are entangled for a stationary observer might look completely different to an accelerating one. This concept, known as entanglement harvesting, pulling quantum correlations out of the vacuum using acceleration, could change how we understand the storage and transfer of quantum information across the cosmos. We are currently transitioning from the age of paper physics to tabletop physics for relativistic phenomena. The Cooperative Unruh detection proposals transform a problem of brute force, requiring infinite energy, into a problem of precision, requiring exact timing and control. In laboratories around the world, vacuum chambers are being prepped. Arrays of mirrors are being aligned with nanometer precision. Lasers are being tuned to excite atoms into the perfect superradiant state. We are preparing to tickle the void. When that first early flash of light is detected, when the superradiant burst arrives a fraction of a nanosecond sooner than classical physics predicts, it will be a historic moment. It will be the moment we stopped looking at the vacuum as an empty stage and finally saw the actors. We will have seen the acceleration glow. We will have heard the silence of the universe break into a song. And we will know, finally, that even in the deepest, coldest nothingness, there is fire waiting to be woken. This is Fun Facts Online. Thanks for listening.